Okay, I'm recording. I'm going to share the screen. Wonderful. Okay, so I thought I'd start off, as I have for the last couple of years, on climate change, because things are changing through the year. This photo that you can see is a real photo. It's not made up, and it really says a lot about the system that the process we're going through at the moment. I've added some photos, recent ones. If you remember the Maribyrnong flooded, this is I know that was a helicopter or some other version, but you can see a huge amount of water where there shouldn't be water. Some Queensland flooding. Lismore. I just went searching for photos, and this one was amazing. I hadn't seen this one before. And Lismore is north of New South Wales. Okay, if you have a look at these maps, going back 4 years, 5 years, this map of Australia, it shows just move this over. It's called the percentage of mean rainfall. So the brown color ones is only 40% of what it used to be, and this little bit of greeny area on the in WA is increased for some reason. And this is 2018, and compare that to what we had in 2010 and 2016. So I call it a short history of Australian drought. And this is some poor farmer in his lake, in his pond. So to understand what happens in Australia, the Australia was divided into a number of climate zones. So you can see the different colors here, and there's an index on the right. So you've got hot and humid, warm and humid, hot and dry, with hot, dry summer, midwinter, hot, dry summer, cold winter, and so on, right down to mid-warm summer, cold winter, where basically we are either that or warm summer, cold winter. And things have changed according to this. Things that are like, I'm moving here. I've got to move this. I've got to all right. So we've got the average daily maximum temperature in February. And if this is average, it's based on 1961 to 1990. So they take a 30-year band, and that's sort of the standard, 61 to 90. And they take an average, and then this is what the average is at the moment. Sorry, this is what they're expecting. And for February, I picked February because we're in February. So we're expecting a temperature down here in Melbourne of somewhere around here, 21 to 24, as an average. And then down here, the maximum temperatures, this is in January 22, a year ago. And compare that to the February one, it's quite different. But also compare it to the zones in the first map. It's very, very different. And so things are changing. So this is, the top one, of course, is an average. This is how we are now. So this is the 28th of January 23. I couldn't get much closer than that. So this is where we are currently. It shows the temperatures. If you look at this, I mean, I've put all these on your notes, and you should be able to see it quite clearly. And if you want more, I only picked a few, but if you want more, there's a lot of this on the web, on the Bureau of Meteorology website. It's absolutely excellent. You just go down, open it up, and the bottom left, look for climate change, and there's a lot of stuff there. Okay, so fires around the country, December 6, 2019. We all remember that, I'm sure. Very unusual. But look at all these fires. We didn't even know most of them existed because we were so worried about this corner here. And a few fires, so it went for a long, long time into 2020. Things are changing. So that brings us up to some questions that need to be answered. So the definitions, what's the difference between weather and climate? What is climate change? What is global warming? What causes global warming? The effect it does, what effects does it have? And what evidence is there? And what can be done about it? So I'll answer those questions as we go. So the difference is very simple. Weather is short term. So at the moment, it's about, I don't know, 20 degrees. It's cloudy. You can see a little bit of sky. I'm looking west. So it's very short term. It's the degree to which it's hot or cold, wet or dry, whatever. It's what's happening now. That's weather. The climate describes the weather over a long period. Maybe I should highlight this long period. And long period in a specific area. So there's a big, big difference. Weather is short-term, climate is long-term. So the most general definition of climate change is the change in the statistical properties, because of the stats that we use are an average, generally the 61 to 90, and then we compare. Now, you can compare what happened in the 18th century, 19th century, because the records around the world of those, even what happened in the mid 2000s. Then, so you get fluctuations. You go up and down, but it's really the overall situation looking at time. So over some periods, like decades, we have El Nino and La Nina, and they are not climate change because they're short term. So we've just gone through 3 years of La Nina, and that's where all the flooding came in, because of the effect La Nina has on the temperature of the water around Australia, of the sea, comes across the Pacific from South America. And that's the problem, but it's short term. We're talking 3 years. It's not long enough. So that's still weather. It's not the climate. Now, global warming looks at the average temperature of the land, the atmosphere, and the waters, the oceans, and the effects that they have. And in the last 10 years, the last 100 years, the Earth's average surface temperature has increased by 0.9%. Oh, I should go back to bed. 0.9 degrees Celsius. Now, for the Earth to change that much is an incredible amount of heat that needs to be put into it. For us, 0.9 of a degree is nothing. I mean, you get out of bed, you take a temperature, and then you take it again at half an hour later, you probably change more than that. So, considering this 0.9, it's quite dangerous. If you consider the amount of heat, the amount of energy that's gone into increasing the surface temperature. So the temperature is currently increasing at about 0.13 degrees Celsius per decade. So in a century, it'll be on average 1.3. Okay, important. So 2/3 of the increase has occurred in the last 3 decades. And that's the scary bit, how fast it's happening. Now, global warming can occur naturally over a bit of time, but there are a number of factors like the Earth's orbit around the sun, because it's not circular, it's elliptical. Sometimes we're a little bit closer to the sun, sometimes we're a little bit further. And also it affects the solar luminosity changes regularly, how much activity the sun has, and sometimes the sun itself gets hotter and then cools down a bit. So the sun's hotter, we get more heat, and so our temperature goes up. But again, it's fairly short term, it's not long term. The atmospheric composition, the various gases that go in, the chemicals that go into the atmosphere, they affect us because they block heat escaping. I'll come to that shortly. And volcanic eruptions. Now, if there are volcanic eruptions, if it's a short one, no effect. But sometimes you get a number of volcanoes erupting about the same time, and that certainly will affect the temperature. Now, the last 3 are basically what affecting. Sorry. The last 3 are the ones that affect our current problem. The variation in orbit of the Earth around the sun is minuscule compared to the others. So I'll say what the variations, the Earth varies in its orbit around the sun. The yellow one is where we currently move. It used to be a little bit closer. If it's a long way away, it gets very chilly. And if the closer, it gets much hotter. And it takes tens of thousands of years to move around, to do this elliptical orbit, about 100,000 years. And we've got evidence of the changes over those periods, and they recycle themselves. The 20th century instrumental temperature recording, which we have, it's showing a sudden rise in global temperatures. It's all happening now, which is a problem. Now I'm going to show you a series of graphs. This one I'll repeat again later. So if you look at what's called solar irradiation, it's in watts per meter square of land. And this dark one is solar irradiance, and the other one's temperature. So the fatter one is 11 years, and this is yearly, the current one. So if you look at, say, the irradiance, how much light, how much heat is coming from the sun, going back to 1880, where they started measuring it, it's wavy, but the general trend is up. And now we're on a downward trajectory. That's the 11-year average. The yearly one sort of is much more erratic, but the 11-year one it is more, you could say, is the one that we really have to worry about. If you're looking at the temperature, however, it's not the sun that's causing it. So it must be something else, and we know what those something else's are. So look at that going up this way. So from 1880 to 2020, 140 years. It's gone up from about 0 degrees to 1 degree. It's a lot. It's a lot. Huge amount. Now, as I said, I'll show you a few graphs. This is the temperature anomaly. Now, the anomaly is how it differs from that average I told you about. So from 1961, 61 to 1990 is the average. So compare them. Once you've got an average, then you compare it to the rest. So this is 1880, up and down. But even in 1940, it starts rising and comes down a bit. But once we get to the 60s, there it goes. Okay, so we've got a problem. Houston, we have a problem, yes. Now, this one there are a couple of little videos here. Let me just show you one of them. You've got all this. Okay, so I started. So 1881 through to 85, 84, 88. And you can see as the colors become warmer, 90s, 1900s, 1917, 18, 20, 23. And look at the Arctic area.
We're not seeing this.
Yeah.
You're not seeing it?
No.
Ah.
You're seeing your screen. Yeah. You need to share that screen.
Yes, I need to share it. You're right. You're right. I will have to get out of it. Hang on. I'm trying to remember how am I going to do this? Okay, I've clicked them. I hope you can hear it now. You can see it. Can you see it now?
We're seeing a blank screen so far.
I'm sorry?
We're seeing a blank screen.
Oh. All right, I will leave it then. Now how am I going to get out of this? Stop share. Okay. So I'm not sure what is happening because that worked perfectly well the other day. All right. So I'll move on. Have a look yourselves. It's very interesting. Greenhouse gases are what we talk about, and that's a real major issue. So we have normal gases in the atmosphere, and the mean warming effect is what I say is 33 degrees. We're talking about water, and the water, or the water vapor rather, is a huge part of the greenhouse effect. So when it's even locally, when it's a humid day, it seems to trap the heat. Of course, us humans feel it much more when it's humid, the heat that is, because of the lack of sweat. We produce a sweat, but it's not evaporating, and the evaporation is what causes the cooling. Carbon dioxide is a
Sorry, Ruben. We can't see your screen anymore.
All right, I'll get out of it. I'll try. What shall I do?
Yeah, just share the screen again.
Yeah, okay. No.
Yeah, we can see it now. Thank you.
You can see the globe thing?
Yeah, we can see your screen now.
Okay, now I'll take it back to the beginning.
Yeah.
So you can see the word and temperature anomaly?
Yeah.
Okay, okay. I'm out of practice, I'm sorry.
That's okay.
Okay, so you can see here quite clearly how it's getting more and more, the colors are getting warmer. The 40s, the 50s. And then in the 80s, it'll start getting warmer. And look at the Northern Hemisphere, the Arctic, the Antarctic. And then goes to the current day. And you can see this for yourselves and read it. And along the side here, it's got in Fahrenheit and Celsius temperatures, what the colors indicate. Okay, stop share. So now I need to go back. It's amazing how quickly one forgets. Okay. All right, can you see that? What is climate change?
No.
No, all right. Oh, what am I going to do?
Share the screen again.
Share again.
Yes.
Okay. Which one?
The presentation one.
Yeah.
To
Oh,
bring
yes,
it
yes,
up and
yes.
share it. Yeah. Yes, we can see it now. Thank you.
But you've disappeared. I had some of you on the screen there. All right, so what's the difference? Climate change. Okay, gone through that. Okay. Now, water vapor is there's a lot I can tell you about water, but it's being a vapor, it actually accumulates heat and it traps it in the atmosphere. But the other greenhouse gases aren't there for long, but water vapor is always there, and that causes an issue. And it stays in the air for a bit, comes back to Earth, but it keeps being renewed because somewhere around the world, the temperature is high enough to evaporate seawater and lake water. So there's always renewed water in the atmosphere. Because as it rises and gets cooler, it sort of becomes rain and comes down. So they estimate that water vapor is around, probably accounts for about 60% of the greenhouse effect. And but it doesn't control the temperature. The problem is it's like the CFCs that were over Antarctica, and the UV rays were coming through very strongly. And in fact, just a couple of weeks ago, they were saying that the hole in the atmosphere there is just about repaired because we've cut back on the CFCs. And so the Earth repairs itself if it can. Now, again, the amount of water vapor is controlled by the temperature. So when it's very, very cold, the water can't be in the atmosphere. It drops as snow or as hail or something, but it's not in the atmosphere. So it varies on the temperature. So the water cycle, this is important. So we have water everywhere, but you get an evaporation from an open bit of water. Transpiration, water goes through plants, and then they open what are called stomata, through which they get their carbon dioxide. So the water escapes through that. Every time every animal like us breathes out, we lose a lot of water. So we have, 7 billion people. I don't know how many billions of animals there are. Every time every one of those animals, including us, breathes, we add water vapor into the atmosphere. which goes up, it condenses clouds, rain. When it's cold, it's snow, of course, but then the snow melts and it goes round and round. And in many cases, it depends what a lake has underneath it. The water may just stay there, or it goes underground and then it moves around. So we have all sorts of movements. But the water, it's called the water cycle, and it's a very important concept to have. Now, the greenhouse emissions by gas, of course, the amount is around 65%. Carbon dioxide in forestry and other land uses. For example, with forestry, they often burn off bits of the cut and they can't use. There's a lot of carbon dioxide in the Amazon when the Brazilian government says just cut what you want, have your farms, put your cattle on it, but often they took some of the logs away, but they burned a huge amount, and a massive amount of carbon dioxide went into the air. Methane is from the earth, from decomposing matter, and it's a very light gas. The formula for it is 1 carbon and 4 hydrogens, CH4. Very small, very light, and just floats up, and it is one of the greenhouse gases. Which is, we'll talk about the problem that's arising now with that. Nitrous oxide is another one, and fluoride gases. So these are the gas emissions by economic sector. So look at this: electricity and heat production, 1/4 of it. Agriculture and forestry, I just mentioned, it's about 1/4. The building industry, the transportation industry itself, and then others. So maybe electricity production, electricity is there, but others might, I don't know what there might be, but there are others. The major greenhouse gases from people's activities, so carbon dioxide is the 64%, methane, other gases, nitrous oxide, fluorinated gases. So this is people's activities on an everyday basis. So every time you put your gas heater on, or you're cooking something, the result is carbon dioxide going out. Every time you in the car, a petrol car, diesel car, carbon dioxide is produced. Now, this is a very, very interesting graph. It goes back about 400,000 years. These are from the ice cores in the Antarctic. They go down a long, long way. And then they can measure the amount of carbon dioxide that was in the air at each of the years. So they can work out the number of years by the rings, because when there's rain and there are changes. So you can see right through here, it's under that line. It's never been above that line. So that's 50,000 years. This is the current era, and now we're there. So the scale on the left talks about carbon dioxide levels in parts per million. So this is a very definitive graph. So that down here, years before today, so 0 is 1950. They took it from that. Today would be 70 years later, it'd be higher. But it's only one of those graphs I could find, so I can't get a more up-to-date one. This one here, global carbon emissions by source. So you've got land use, coal, oil, gas, and others. And look at this, 1940, 2040, and then up it goes. This is the annual greenhouse gas index. You wouldn't have seen this before. This is a new way of doing it. I don't know how they calculate the index, but this is just very interesting. From 1980 to 22, so it's, yeah, 22. And then you've got to combine heating influence. What causes it? So this is the carbon dioxide and methane. Then you've got these three others, or there may even be four, according to that, nitrous oxide, CFCs, and these other chemicals that are in the air. Again, 1980 to 2020 and beyond. Excuse me. Now, natural greenhouse effect, we have an atmosphere around the Earth, which is very useful to us, but it also allows the solar radiation comes in and then it escapes again. Some of it, and some of it bounces back. And the greenhouse gases up here are minimal at one stage. But if you go to a more current time, you get the sun with the radiation coming in, the same amount, and it's re-radiated, but it's bounced back again. So it doesn't allow this amount compared to this amount to escape into space. And this is what these gases do. They act as a blanket. Now, what have we done since the Industrial Revolution, so 1760 to 84, what's it, 80 years, the amount of greenhouse gases increasing due to the burning of coal. Once they discovered that with the Stevenson, I'm trying to remember the name of the Scottish guy who devised the steam engine. And once you've got a steam engine, you can attach all sorts of pulleys and wheels to it. And that's when the Industrial Revolution started. So we get an increase in effect of carbon dioxide, methane, ozone. And by the way, ozone, if you don't know, then is 3 oxygens. And normally we breathe in oxygen, which is 2 oxygen atoms. Ozone is 3, and that causes a problem. CFCs and nitrous oxide. So all these different gases. So the concentration of gas of carbon dioxide and methane, which is CH4, these are all small molecules, and they've increased by 36% of carbon dioxide and 148% since 1760. This is in the atmosphere. The fossil fuel production and intensive livestock farming has caused this massive amount of methane. Now, methane is produced during digestion of vegetable matter. So when we fart, we release methane. When cattle and sheep fart, they fart a lot because that's all they eat, grass. And in New Zealand, I don't know if they have, but they were talking a little while ago of actually putting a methane tax on every cow. So it may or may not have happened. So these levels are higher than at least 800,000 years, and I showed it. And as I mentioned, it's from the ice cores near Antarctic. So again, just to show you I showed you this before, human activities. And by the way, 20% of the Amazon rainforest has already been lost. And a lot of it is recent because of, but we've got this new government there, so that's stopping now. This is a major problem with the loss of the permafrost. Now, the permafrost is the the area in the Arctic Circle, which is like land, it is land, but the soil water is permanently frozen, and that's called permafrost. Now, it has trapped for a huge number of years, I don't know how many, thousands of years, a certain amount of methane. Now that this permafrost, permafrost I assume is permanent frost, permanent frozen, as it thaws, this carbon in the form of methane is released into the atmosphere. And the thing is, with respect to the climate and climate change, and this is an example of positive feedback loop. So what that means is, as warming increases, it causes more warming. It loops through it. So when we in physiology, we talk about negative loops, or negative feedback. So so for example, if your blood sugar rises, hormones are released to reduce it. That's negative. So if you do something, the opposite happens. With this situation, the positive feedback is where the next step is higher release than the previous one. It goes up and up and up and up. Here is a graph, a map of the permafrost disappearing. Now, if you look at on the right, bottom right here, you see the remaining, the permanent frost thawing by 2050. That's the red bits along here. You can see how big the permafrost is. The permafrost by 2100, that's all gone by 2100. At the rate, if we continue increasing the rate of climate warming. Now, remaining by 2100, maybe that amount. We don't know. But if you think about the north of Europe and Asia, all that, most of the orange and the red, will be land again. But all that is releasing the trapped methane, which is a problem, major problem. Now, this is a satellite photo. If 2022 summer minimum. So sea ice concentration here, you can see down the bottom in percent. Now, the median in yellow here, 1981 to 2010. This outline is where the sea ice used to be. And this is where it is now. And it's not good, not good at all. I'll come back to that a little later. Here's the Arctic sea ice, the yearly minimum ice, because it changes every year, because some melts and then it refreezes. So the minimum extent in millions of square kilometers is on a downward trend over the last 40 years. Is the permafrost in Alaska. So this is the Seward Peninsula. So here is Alaska. There's the Panhandle, and this is the Seward Peninsula up here. So this shows you, well, you start with the yellow. This is a continuous permafrost with a little bit. This is what's happening. There's no permafrost there, and there's some in the blue. Later this century, they estimate there'll be no permanent, except tiny little bits, and mostly red and blue, either some or none. The effects that global warming will have, there are many, many effects that will occur. The spread of disease. As it gets warmer, insects like mosquitoes, for example, and other insects will easily spread disease. We're at 7 billion people at the moment. There'll be problems with amount of water that's available. There'll be a lot of migration because of that. Food they won't be able to produce, so they move on. And then one country says, I need to go into your country. Conflict, wars, the polar ice caps are melting. The increase in severe weather, I did mention, increased probability of intensity of droughts, definite. Heat waves, definite. Economic consequences, because you can't produce when you don't have enough water. You just can't produce. There'll be more floods, but then they wash everything away. More bushfires, more deserts, loss of biodiversity, animal extinction, the death of ocean life, and the thawing of the permafrost, or the tundra. I should mention ocean life as the oceans get warmer, there's less oxygen in the water. Cold water holds a lot more oxygen, a lot more gases, if you like, than warm water. That's why there's such a propensity of sea life around the Antarctic as compared to the Pacific. And the other thing is, as it gets warmer, it absorbs more carbon dioxide, so it becomes more acidic. And that causes problems with animals with shells of various sort, because the calcium carbonate, which is dissolved by acid. We have a thing called the global ocean conveyor belt. Now, this up the top where the water's cold, and around the middle where the ocean's warm, there are these huge, absolutely massive currents that go through. And there's one here in the Atlantic, comes from the Indian up there, it goes around to say Western Europe, England. Some of it goes a little bit further, but then what happens is, because this is warmer, it stays on the surface of the water. But as it gets to the colder water, the water, that warm water, is cooled down, and it takes a dive, and it goes down into deep down, comes back and does the route again and goes back. Now, unfortunately, as I mentioned before, the Arctic ice is melting. And instead of diving down the water and cooling and bringing back all the nutrients from underneath to this area, the water keeps going over the top. So the fishing, the fish don't have enough food. And so the fishing industry is now in great distress in this area. I don't know anything about this area around the north of the Pacific, but here it's really bad. Now, I won't try showing you another video, but this is a very interesting video of how this works. I recommend you watch it. Now, the retreat of glaciers at sea ice is a problem. And this is the evidence, some of the evidence that we have. The Fox Glacier now terminates about 12 kilometers from the Tasman Sea. We were there, I think it's 2018 or 19. We were there first in 1975, and the Fox Glacier came to almost the sea. And the car park is still the same. So you have to walk for half an hour to get to the edge of the glacier today. We have a decline, a 10 to 15% decline in the Arctic sea ice, and 40% in the average thickness. This is the Arctic sea ice. Okay, so a lot of it's gone. In the Alps, Australian Alps, the snow depth at the start of October, so the end of winter, has declined 40% in the last 40 years. Average sea level has risen about 20 millimeters per decade over the last 5 decades. Now, 20 millimeters doesn't seem much, but overall, it really, really is, if you consider the tides. So if you look at global sea level from 1880 to 2020, little bit, 22, I think you see very, very clearly the rise of the height of the sea. These last bits here, I think they're the ones that were taken by satellite. What evidence is there still? We have changes in the mating and migration times of birds. So it's all over the place. They don't know when to go, but they work on temperature and light, amount of light. Whole altitudinal shifts of plants and animals, especially in the alpine zone, the plants are moving further north because there's less ice, and the soil becomes friable, so the roots, they can put roots down. It's not full of ice. Tropical fish are now found off New South Wales as far as Eden. The Irukandji sea jellies are now on the Sunshine Coast. They only used to be far north Queensland. There's an increase in coral bleaching due to increased water temperature. And what that means is that now coral is an animal. The color that the coral has, is due to algae. So there are different color algae which go to certain types of coral. And as the water temperature increases, the algae are expelled. And eventually, the coral will be okay for a year or so. But if it keeps on going, it requires the algae to help feed it. They have a symbiotic relationship where the coral looks after the algae and the algae produce food for the coral. And then eventually the coral just dies. The algae just goes somewhere cooler. And of course, the thinning of shells, which I mentioned before. So you have, with the increase of carbon dioxide in water, you get acid. And acid eats away shells. So lobsters or oysters or whatever type of shell they've got becomes thinner, and the animals become more fragile, more easily eaten by other animals. So evidence, the ice cores, and so the ice sheets have a very special property, because as snow drops, it traps air, and as more snow falls on top of it, it's compressed, but the air is contained. And so they can sample the air that's accumulated at each level. They can work out the air temperature, the air chemistry, from whatever time you're looking at, and they can generate a continuous history of what's going back. So they can go back about 800,000 years, and those graphs I showed you before, and it will be again the next one, the same one, is where all this comes through. So these ice cores can go down to 3 kilometers in the Antarctic, and so they can basically compare concentrations of greenhouse gases then and now to temperatures of then and now. So it's amazing stuff. So this is the graph I showed you before. By the way, the source of this is NASA. and hang on, I forgot to open this up. So we've got yeah, you can see it quite clearly. These are the major centers for data gathering. So in the UK, they're mostly in England, in America. They've got remote satellites, which sends. There's Earth System Science Center in Alabama, the US Meteorology Office, the Air Meteorology, CSIRO. In England, they put it together with one called the Hadley Center. And so they looked from 1850 to, this is about 2000. This is an older graph of 1990. Go higher, a bit further. The records that they have been keeping from all these. So the British one has been the longest one, but they follow the same trend. And that's basically what this graph is showing. And this is the surface and global surface anomaly of using satellite data, and there are 5 different ones here. And again, they're up and down, they vary a little bit, but the trend is definitely there. The past 8 years have been the hottest on record. This was the headline about 3 weeks ago. So since 2015, the warmest have been since then. 16, 19, 20 are the top 3. And that's from the World Meteorological Organization. These temperatures, they change between years, okay, and up and down, But since the 80s, every decade has been hotter than the one before, as the prediction showed. And the hottest ever, the oceans were also hottest ever in 22. So last year, the oceans worldwide were the hottest. And the excess of heat in the atmosphere is absorbed by the ocean, of course, and the temperatures. So the temperature of the water is a major climate change indicator. Here's global land temperature increasing. Here's global land and ocean. So sort of averages from 1880 to 2000, and you can clearly see. But these are the anomalies. So the anomalies are set from 61 to 90, so 30 years, and then they're compared with that average for each of those years. So they took the average temperature for those 30, and then everything else compared. So from whatever that might be, in the late 70s, it's on the up and up. But it changed every year, of course, but it keeps going. Climate models, 1861 to 2100. And these are the variations. But again, so these are, the black one is the estimate, that's the average, and the estimated average going up. Now, the trend in Australia, so instead of using 61 to 90, they're using 70 to 20. So a 50-year average. It's a bit different. And this is all satellite based. So you can see how we're what the temperatures are. It's a trend, okay? Maximum temperatures. So in down here where we are is around here. And that's an increase of degrees centigrade or Celsius per decade. Okay, so this is the trend in minimum temperatures. So we're still increasing the minimum temperatures. Hang on, am I going the wrong way? No? Okay, so this is the trend in mean temperature, so the average day-night. So of course, if the day and night are both increasing, so is the trend. Except for some reason here, the Northern Territory, the blue is reduction in temperature. The annual temperature in Australia, 1910 to 22. This is an interesting diagram of what Australia looked like temperature-wise, the annual average land temperature from 1910 to 2019. And if you look at it carefully, you'll see as time moves on, there's less and less green, which is the cooler temperature, and more yellow, more and more orange, more brown, more red. And it's finished in 2019. Sea levels are also rising. Now the factors in sea level rising, so as the planet's warming, the oceans have for a long time have been a buffer. They sort of absorb the heat, so the Earth doesn't, the overall temperature doesn't rise too much. But as the oceans increase in temperature, they expand. So by expanding, they become higher. There's more volume of sea. So it's called thermal expansion, and this is a major cause of sea level rise. And the other contributor are the glaciers and the ice caps. They're melting. So the water, this fresh water, is added to the seawater. And that where the fresh water is coming in is causing problems. Now, as the sea levels are rising, the global average has risen 20 centimeters, 8 inches in the old currency, from 1870 to 2018. Now, that's a huge amount. This is the global average. The seas and oceans are moving up and down all the time, but the average is increasing, which is terrible. And during the 20th century, it increased 1.7 millimeters per year, but it's cumulative, so it's causing issues. So from 93 to 2018, it was increasing 3.4 millimeters per year, so double. So if that rate keeps on going, by 2100, the seas, the oceans will be about 20 centimeters, 25 centimeters higher than they are today. But a continued acceleration could cause it to be 65 centimeters. If other factors come in, the waters will become even more. Here's some photos from Italy. a little flood. The global sea levels. These are mean sea levels again. I'm just showing you that there's so much information out there. Yeah, here are the figures I gave you before. Now, I'll see if I can get this to work. I don't know. I'll give it a go. Come on. Oh. Now, can you share? Now, can you see this? Can you see this picture? Can someone tell me?
Yeah,
Oh,
we can
good.
see Coastal Risk Australia.
Yep, good. So what this is an Australian program, and you can put in any place along the coast and it'll show you what happens. So if we go to say Brighton, Victoria, what happened to it? Brighton, Victoria. It should be coming up. All right. I'll go to another one. Close. Okay, here's Byron Bay. You can do this, play with this yourself, and you can all right, where do you want to look? Now, I was playing with this the other day, and it showed me. Oh, okay, here we are. Current day. The highest tides today would cover this amount of water. But I think there was a little line there that I don't know. If I can move it around, you can see how much this would be inundated in 2100. If we go to, oh, it is manual. That's what I was looking for. So if we go up, say, let's take it 2.2 meters. If you know Byron Bay, this will show you the how much of the coast is covered by water. If we go down to okay. I don't know why it's not going. Okay. This is online, so it's not, there may be a problem somewhere. But I can't see where. But all down the coast here, you can see how it's inundating. I'll make it smaller, easier. So where are we now? Oh, there you go. Okay, here's Malakuta. Here is Golden Beach, Wellspool. There's Melbourne. Normally it just goes to wherever I want to go. Now this area here, Aspendale, Chelsea, Long Beach, Carrum, Seaford. If the seawater went up 2.2, let's make it just 1. 0.9. So little bits on the inside, you can see there's a bit of water there. But if we increase it, it's a fine line. If we go to the city, Williamstown, well, these are 2 meters. Look at this, Point Ormond, Elwood, St Kilda. So all this will be underwater, not the city itself, because it's a little bit higher in parts. So I want to spend more time on this, but it's very interesting looking at this this program. Now, okay, so let's move on. Rainfall and extreme weather, they're changing. So in the last 50 years, we had fewer cold days and nights and more hot days, hot nights and heat waves. Heavy rainfall events increasing. Since 1990, precipitation has increased in eastern parts of Americas, Northern Europe, Asia, and Northwest Australia. Reduced precipitation or rain has occurred in Central, Southern Africa, and they've got major famine issues, Mediterranean parts of Southern Asia. Since 1950, Eastern and Southwestern Australia have become significantly drier. So it varies where you are, but things are happening. Now, this is the rainfall anomaly. This is the most up-to-date. This is at 22. Can't get any better than that. And if you look at this, some years, annual rainfall are much less rain than, and these have more rain. So last year, it rained a lot, maybe before. 4 years ago, 5 years ago, it was very dry. Back here, about 70, 75, we had major floods then too. You can see with that. Sea surface areas, this is up to 21. So this is the annual, these are the trends, how the surface temperatures are increasing again here in the Eastern Australia, northwest of Australia. The only thing here is a little bit of purple down the bottom, and this is where it's reducing, not increasing. Here are, and this is the world temperature. Here's Australia, South America, North America, Europe. But look at this, along here, the heat there and there. So these are part of the problems because there's the currents that come up from the Antarctic come through, but they pick up the heat and they keep moving out towards us. And that's causing issues. These are 2005 and 7 monthly average. And this shows you the temperatures down the bottom. This is quite a scary map. And this one is the temperature on the 10th of February 2020. So the water temperature, this area, 26 to 30, here in 32, very high. Then we've got this newspaper cutting. Climate change is hitting fish stocks in Tassie. So we have along the way, look at the temperature, water temperature around Tassie. The warmer the water, the less gas it holds, as I mentioned that before. So the warmer the water, fewer fish will be found. It's overfishing. It's not the right temperature. Now in Greenpeace, they found new penguin colonies in places they didn't expect to find them. So the Gen 2 penguins are usually in the warmer part of the Antarctic. The found was too icy to successfully raise chicks. So where it gets too hot, most places in some parts of the Antarctic, it's too cold. Excuse me. Now, before this happened, the 75, there was only one solitary Gen 2 nest on that island, and now there are 75 because it's warmed up. The Arctic ice has declined from 84 to 16. And this ice has declined from 1.9 million square kilometers to 110,000. And the ice that's built over many, many, many years tends to be thicker and less vulnerable to melting than newer ice. Okay, so we've got a picture of this. The blue-gray is the young ice and the white is the older. So there's your old ice and the new ice. And this is what it is a couple of years ago. The ice is gone and not much. The white is the older one, I think, wasn't it? The blue-gray is the new one. So that's all new. And there's only a little bit of the old ice left. May I suggest you watch these? I put the times on them. What the Earth would look like after all the ice melted. Very interesting with both of these. The IPCC, and it's a report from 2018 about human influence. I won't go through this now, but I'll give it to you. But can we limit global warming by 1.5 to 1.5 by 2100? So, reduce electricity production through the use of coal. Necessary. It's just so important. If we keep producing electricity with coal, the temperature could rise to 2.4, I mean, it's about that much, and maybe by 21 to 4.4, which is crazy. What can we do? We need to stabilize it. 450, 550, it's about twice from the pre-industrial levels, and many scientists believe the most damaging impacts of the climate can be avoided. We can keep it out of that, and it's currently 0.9, as I mentioned before. So current concentrations are about that. And global CO2 levels are running at about, were running at about 280 until 1850, when really started burning coal like crazy. So from 280, we're up to 400. So we would have to reduce the greenhouse gases by 50% to 80% to what they are on track now. But some countries are still increasing their use, and China is building more power stations. They need coal and so on. What we can do? Increase wind and solar power, hydrogen produced from renewable sources. It's called green hydrogen. There's biofuels like E10 petrol, and wave power, which is amazing. Nuclear power. The problem with nuclear power is what you do with the the waste, and also takes decades to put it together, the whole thing. There's also potential of carbon dioxide emitting from fossil fuels and stored underground. It's called carbon sequestration. It stores it. However, it's not, hasn't been particularly successful at all. It escapes. What else can we do? We can reduce the gases we emit, and let's go to that same. Now, we need to plant more trees and plant more seagrass because they absorb carbon dioxide like crazy. And that's a biological sequestration. Increasing forest lands, change to farming practices so we can absorb more carbon dioxide and then store it in the plants. Here's a photo from Sweden. And they had a cold snap a couple of years ago. And this dog and his leash was stuck in the ice. And then, as were all these fish. Now, you probably heard last week about this cold snap in northeastern America. And basically what happens is there's a stable polar vortex and there's this cold air constantly. But with air pressure changing, you get warm air moving up and pushes this up, so the cold air comes down. So you get these strong jet streams, instead of going just around the Arctic, come further down, and they go through. And this is an exaggerated map, fit it in, but then Northern America, it's cold snaps just for a couple of days, but it's very, very, very cold. They went down to -40. Now, with human health, we've got to be careful. We have biodiversity loss and ecosystem function, and what will happen when there's freshwater decline, we get desertification, we get climate change, with various things. Human health is will be affected because we can't produce enough food. People are displaced. There's less safe water to drink, decline in several ecosystems around the world. And with ozone depletion, which this is an older plan, which isn't relevant at the moment, but for some reason, if the ozone depletes again, then UV exposure become greater. So if there's less precipitation, then we've got less water. It's all interlinked. There's some further reading if you like. This is worth looking at. Just copy this link and paste it. I've given to you a couple, just to finish off. I like to include a couple of cartoons if they're relevant. It said, rising sea levels finally extinguished the last coal plant. Says, this guy says to this one, see, I told you climate is self-correcting. Global warming is a complete myth. So just keep walking, but stay away from the edge. So we still have quite a few people who believe in the flat earth theory. Remind me again why we should fear global warming. Our igloo melted. The scientists assessing the impact of climate change, the politicians. And we even hear it today. And if you remember that picture at the beginning, someone drew this cartoon. What more must I do to convince you idiots? Love it. So in the 70s, climate change is coming. And the 90s and the 2000s, climate change is here. And let's say, wow, I didn't see that coming. And that's it. So guys, I've lost a lot of regards. Obviously, they weren't interested in what I was doing, but you're welcome to put your you can unmute yourselves if you like, and we can talk about anything you want to talk about.
Ruben, sorry, I'm a bit lost. What's the CFC stand for?
Fluorocarbons is the FC part, and chloro as a chlorine, chlorofluorocarbons. So the gases we used to use. So if you had a fly spray, for example, the liquid that that used to spray out, the gas that was in the can to spray the liquid out were the CFCs, but they broke the ozone layer down.
All right, that's what it was. Thanks. Okay.
And refrigeration.
It was very much in refrigeration, yes, but that doesn't exist anymore. They use something different.
So what do you think, Ruben? What hope have we got? I just don't know what to think anymore.
I don't know. It's really hard. I'm more worried for my kids and my grandkids, but it seems to be easing off because more and more countries are
taking notice.
Yes, but I don't know. It's really hard to know. Really hard to know. The Earth has gone through warming periods and cooling periods. We've had ice ages, it might. If we disappear, the Earth will just sort itself out and readjust. It's the money, it seems to me, that's driving factor, isn't it? To some degree, yes.
Yes.
I mean, we've put on, we've got solar panels and a battery. So we don't use any electricity from the grid.
Okay.
So in summer, we actually get money from the electricity company. In winter, if the battery doesn't charge up fully because of cloud cover, it costs us a little bit.
Wow.
There's enough there. Because winter, you not only use everything, but you've also got heating.
That's right.
Yeah. And we've got no gas. We've got gas hot water, which when that dies, we'll put electric hot water in.
Wow.
Instant hot water. That's what we've got. Yeah. So it's good. But I think some of the guys, new people too, have left. Maybe they thought this is not biology. It really is biology to a great degree, just from a different angle. Sorry?
It's survival.
It's survival stuff, yes. I can't remember what I'll do next time. Next time. What's the date today? Anyway, okay, there'll be a lesson next time in two weeks, but after that, we'll be in Tassie for a couple of weeks, so I'll be missing 1 week. Okay, so all right, well, let's leave it. Unless you have a question or comment.
Thank you very much. Really.
Sorry about the confusion at the beginning, but
Right.
Okay.
Thank you.
Thank you,
Thanks a
Ruben.
lot.
Thank you.
Very good.
Thank you,
All
Ruben.
the best. All the best. And we'll get down to what people call biology next time.
Good on
Thank you.
And congratulations for your Australian medal.
Thank you. Oh, you saw it. Yeah,
Congratulations.
that was good. I'm pleased. I've been recognized.
Very good. Thank you. Bye-bye, everyone.
Bye, Preeti. Bye.
Bye.